This is chapter 3. In this chapter, we discuss torsion. This is the 13th session. To start with, we introduce torsion, discuss shearing stresses due to a torque, and obtain the torsion formula. This is an overview of the sessions covered in the first 4 chapters again. It gives us a general view before we start looking at the specific session at hand. We'll now look at session 13, which is one of the 4 sessions under torsion. Here we introduce torsion. Earlier we dealt with bars subjected to axial loads and discussed stress and strain in such bars. In this chapter, we'll discuss different types of components subjected to torsion. We'll look at stress, strain, and deformation of such components. We start with circular bars. We have a circular bar of constant cross section AB to which a torque T has been applied. The end B is fixed and will not rotate with the application of torque at A. From physical understanding, one would think that application of a torque at A will twist the bar. A rectangle CDEF on the surface of the bar. The rectangle CDEF can be considered consist of rectangular elements. We have taken vertical and horizontal lines as shown to depict the elements. This is the case before load is applied. After torque is applied, based on physical understanding, one would think that the vertical lines will not change. However, the horizontal lines would change in angle. Consider the shaded element shown here. All the angles are right angles before application of the torque. After application of the torque, these angles change from the right angle values. Hence, one can conclude that this element has undergone shearing strain. Thus, application of a torque causes shearing stress and shearing strain. In this diagram, same circular bar is shown and a torque is applied. And we have shown a circular section, that is a plane section. Based on heuristic arguments, will show that this plane section remains plane after the torque is applied. We'll also show that there is no distortion within the plane section. We can think of this bar as consisting of infinitesimally thin small disks. Then under torsion, these disks rotate with relation to each other. Since plane sections remain plane and there is no distortion within the plane. We now show that plane sections remain plane when torque is applied. So this again is a circular bar of constant cross section. We applied a torque T on the right side. Considering equilibrium, a torque will act on the left side in opposite direction. A circular section and 2 points in the circular section D and F. Let us assume that after application of the torque T, the 2 points D and F move to the points D dash and F dash. Since the circular bar is axisymmetric, D dash and F dash will again be on the same circular sections as shown. Also, due to axisymmetry, the distance between D and F will be the same as the distance between D dash and F dash. Now let us look at this bar from the right end. An anticlockwise torque has been applied from the right end. If we look at the bar from the left end, we also see that there's an anticlockwise torque acting. So the conditions from the right end and the left end are exactly the same. In this figure, we have shown that the points T and F move away from the right end and towards the left end. One can argue that there is equal reason for the points D and F to move away from the left end and towards the right end. These conflicting arguments would suggest that the points D and F do not move at all, either to the right or to the left. They stay in the same circular section. Hence, we can say that the plane of which the points D and F are a part of remain plane after the torque has been applied. Hence, our assertion that plane sections remain plane. In the previous slide, we used heuristic arguments to show that plane sections remain plane after a torque is applied to a circular bar. Here we will show that within a given plane there is no distortion. So as earlier, we consider a circular bar to which a torque P has been applied from the right side. Due to equilibrium, we see that an equal and opposite torque must act on the left side. Let us consider the section AA as shown along with the concentric circles. To start with, let us look at this bar from the right side or the right end. Let us assume that there is angular distortion within the plane AA. We consider that the outer concentric circles undergo greater angular rotation than the inner concentric circles. Then a straight line should bend as shown to the left. Now let us consider the same problem from the left end. In the left end, the torque also is acting in an anticlockwise direction. Here again, We considered that the outer concentric circles have greater angular rotation than the inner concentric circles. Then a straight line after torque has been applied will bend as shown towards the right. The conditions from the right end is exactly the same as the conditions from the left end. When we consider these two cases, there is contradiction. Due to this inconsistency, we have to conclude that a straight line after torque has been applied remains straight, which means the angular rotation of the different concentric circles remains the same. Thus, there is no distortion between different parts of a given plane. We have thus established, using heuristic arguments, that plane sections remain plane in a circular bar subjected to torque, and there is no axial movement. We have also established that there is no distortion within a given plane. As earlier mentioned, this means that the bar can be said to be comprised of infinitesimally thin disks that rotate in relation to one another when torque is applied. Here we have a circular bar of constant cross-section and length L, to which a torque P has been applied on the right end. The left end is fixed and does not move with the application of the torque. AB is a horizontal line on the surface, which after application of the torque moves to A B dash. So the point B moves from B to B dash. We consider four circular cross sections at infinitesimal distance to each other, as shown here. We consider two rectangular elements on AB between the disks. With the application of the torque, the elements are now adjacent to A B dash. The angles at the corner of the elements has changed. The change in angle is the same for both the elements and is given by gamma max. If we had two circular cross sections infinitesimal distance apart near the point B, then an element on the line AB, like these elements, would have undergone the same change in strain. Consider a section taken perpendicular to the axis near the point B. Then the internal torque on that section would be T. If we take a section near the left end that is perpendicular to the axis, again the internal torque acting on the section would be T. So along the length on any perpendicular section to the axis, the internal torque acting is T. We can therefore think that the strain will be same along the length as we have just seen. Earlier we saw a bar subjected to tensile force with an increase in length. Each unit length of the bar contributed equally to the overall increase in length. The overall increase in length was a summation of the increase in length of each unit portion of the bar. We can consider this circular bar to be made of discs, each infinitesimally thick. Then the total rotation at the right end is a summation of the rotation of all the discs from the left end to the right end. We earlier showed that within a given plane of a circular bar subjected to torque, there is no distortion. So if OB is a straight line, then after application of the torque P, it will still remain a straight line. Here we get the line OB dash after application of the torque. Now consider an inner concentric circle shown by the dotted line on the right end. Also, an inner concentric circle of the same radius is drawn on the left end. Let the point where this concentric circle cuts OB be denoted as D. An equivalent point on the left end is denoted as C. So the straight line CD is parallel to AB. We earlier mentioned that the straight line OB after application of the torque becomes OB dash. That would mean that the point D now moves to point B dash. The corresponding strain gamma, as we see, is due to D moving to D dash. Here we see that D dash is less than B dash, while CD is equal to AB, which means this strain gamma is less than gamma max. If we had taken a concentric circle of a smaller radius, then gamma will be still smaller. So we can see that at O, gamma would be 0, and it will keep on increasing till we reach the outer edge. Now tan gamma max can be given as B dash by AB. AB is equal to L, so gamma max can be given as B dash divided by L. Considering gamma max to be small and tan gamma max equal to gamma max itself. Now B dash is equal to phi into OB. OB is denoted as C. So that would mean B dash is equal to C into phi, which would mean that gamma max is equal to phi C divided by L. We can similarly write gamma is equal to D dash divided by L. Now d dash is equal to phi into OD, where OD is denoted as rho. So d dash is phi into rho. This gives gamma is equal to phi rho divided by L. Considering the equation of gamma max as 1 and the equation of gamma as 2 and dividing both sides of the equation, we get gamma max divided by gamma is equal to C divided by rho. If we consider rho as a variable, then gamma also would be a variable, and gamma max and C are constants. So gamma would vary linearly with rho. So gamma would be 0 at rho, and very linearly till we reach the point on the surface. As long as deformations are small, the assertions that plane sections remain plane and that there is no distortion in a plane when a torque is applied to a circular bar remains valid. This is shown by other considerations. Based on the assertions, we develop formulas for stress and deformations. Using those formulas, we can find stress and deformation for practical cases. Experiments carried out using the same parameters match the values calculated. The assertions can also be proved using the mathematical theory of elasticity. Circular tubes are similar to circular bars in many respects. Circular tubes are also axisymmetric like circular bars. If the inner radius is R1, then the strain at the inner radius is given as phi into R1 divided by L, where phi is the angle of twist and L is the length of the tube. Similarly, the strain in the outer surface with the radius R2 is given as phi into R2 divided by L. As in the case of a circular bar, the strain varies linearly from the inner radius to the outer radius as shown. Now, using these two equations and dividing both sides, we can see that gamma 2 by gamma 1, that is the strain at the outer surface to the inner surface, is equal to R2 divided by R1. That is the ratio of the radii. Here we discuss shearing stress due to torque. Till now, the discussion has been on shearing strain only. However, we know that the Hooke's law of shearing stress and strain gives a relationship between strain and stress. This relationship is applicable if the proportional limit in the stress-strain curve has not been reached. The relation is a linear relationship. Tau is equal to G into gamma. We earlier found out that for a circular bar subjected to torque, the strain varies linearly from the center of the bar to the edge of the bar. Also, we know the relationship between stress and strain is linear. This would suggest that the stress also vary linearly from the center of the bar to the edge of the bar in a circular bar subjected to torque. So tau here is given as G into comma as explained. The relation we earlier found of strain was phi into rho divided by L. Now if we put this equation into the relation of Hooke's law, then we get tau is equal to phi rho G divided by L. We also earlier got the relationship gamma max is phi C divided by L. Again, if we put this relationship into Hooke's law, we get the relation tau max is equal to phi C G divided by L. Now dividing both sides of equation 2 by equation 1, we get tau max divided by tau is equal to C by rho. We earlier found a similar relationship involving strain. The ratio of stress is the same as the ratio of strain. We'll now examine the relationship between stress and torque. We take a circular bar which is fixed on one end and a torque is applied on the other end. A section ABCD is taken. We have separated here the left hand portion. So a torque must act on the section so that the whole left hand portion is in equilibrium. Looking from the right end, this torque is in anti-clockwise direction. This torque would be made up of stresses acting on the whole section of the circular bar. These shear stresses acting at all points of this section except the point O will make up the torque. It varies from 0 to a maximum value on the surface. It does not only act on these 5 radii, but it will act on every radii of this circle. So it does not only act on OE or OF, but every radius of the circle. Here we obtain the torsion formula. Earlier, using heuristic arguments, we found out the variation of strain in a perpendicular cross-section of a circular member. It was found that the strain was 0 at the center and was maximum at the outer surface and varied linearly from the center to the outer surface. Hooke's law gives a linear relationship between stress and strain. Hence, it was found that the stresses also varied linearly. The stress at the center was 0 and the stress at the outer surface was maximum. The stresses will vary in this manner throughout all radii of this cross-section. Hence, the stress at a given radii would have a constant magnitude. Hence, the stresses on this annular ring would have a constant magnitude as well. Here, the same section with stresses acting is shown. We consider an annular ring with infinitesimally small thickness and its area given as dA. Let us consider small arc of this annular ring. Then the force acting would be dF1, or the force is denoted as dF1, and the moment would be dF1 into rho about the center. We can consider another small portion of the arc. We can consider that the force acting would be dF2, and then the moment would be dF2 into rho. In a similar manner, we can find forces of small portions of the arc throughout the circumference and find out their moments about the center. So the total moment that acts about the center due to stresses acting on this annular ring is dF1 plus dF2 plus other dFs into rho, which can be given as dA into tau into rho. We can consider other annual rings with stresses acting on them, and they will give moments about the center similar to this annular ring. Summing up, the moment due to stresses due to all annular rings give us the total moment acting on this area and be equal to the internal torque that is acting. This is the corresponding relationship. Here A is the total cross-sectional area. Now tau, as we have earlier found, has a relationship with tau max as shown here. So tau can be replaced by tau max into rho divided by C. So in this equation, we have replaced tau by tau max. Part of this expression now becomes rho square dA integration of the whole area, which is the polar moment of inertia. So now tau max can be written as EC by J, where J is the polar moment of inertia and C is the distance farthest from the center. Here we find the torsion formula for a circular tube. The inner radius is R1 and the outer radius is R2. Like in the previous case, we consider an annular ring of area dA. Then the moment due to the stresses acting on the annular ring would be dA tau into rho. And also the relationship between the stresses acting on the section and the internal torque would be the same as this expression, except that the area has changed now. Here we write the area dA in terms of d rho, which is the thickness of the angular ring, and its circumference, d pi rho. So substituting this value in this equation, we get this expression where the integration now is of rho square, and the limits are r1 and r2. As before, tau can be written in terms of tau max, and we have replaced tau in this equation using the expression related to tau max. As we can now see, we have a function rho cube now, which we integrate. As such, part of the expression after integration is given as r2 to the power of 4 minus r1 to the power of 4 into pi by 2. Now that part is the polar moment of inertia of a circular tube. So here again we can give tau max as equal to v r2 divided by j, where j is the polar moment of the circular tube and r2 is the outer radius. With circular bars subjected to torque, till now we have taken sections perpendicular to the axis of the bars, and we have found out the shear stresses on this section only. As we earlier discussed, shear stress occurs in force, so 4 shear stress occur at the same time. Here we'll discuss the other 3 shear stresses that act. Let us consider a circular bar of constant cross-section. A torque is applied at the end A. Considering equilibrium, there must be an equal and opposite torque that would act at B, as shown. This is the same bar AB. Here we have taken a section CC perpendicular to the axis of the bar. We consider equilibrium of the portion to the left of the section CC. So there's a torque acting at A. There must be another torque acting on the section to balance the torque at A for equilibrium. If we look from the right side, the portion to the left of CC, then we see that this torque is acting in an anti-clockwise direction. We consider the face of the bar nearer to us as the near end and the face of the bar on the further side as the far end. The torque acting at CC is comprised of stresses acting on the section CC and is shown in this diagram. This is the near end, so this is the near end, and this is the far end, or the end that is at a distance. We can see that the stresses here also cause an anti-clockwise torque. Now let us consider an element on the far end on the section CC. This is the same element. On the far end, The stresses must act in the upward direction so that the overall torque is anticlockwise. Here we have given a magnified view of this element. Now at the section CC, the stress acts upwards. Here, this is the section CC, and here tau xy acts upwards. This tau xy is this tau xy. And these are the two other shear stress, tau yx, that acts perpendicular. Considering equilibrium of this element, we know that these two tau xy has to be of equal magnitude, and the moment created by tau yx has to be equal and opposite to the moment created due to tau xy. Earlier we took a element on the far end. Now between A and CC, we have taken a chunk out in the near end. So here we can see in the near end the shear stresses are acting downwards. Also here we see the shear stresses acting downwards. Because we have taken the chunk out, we can see the shear stresses that are acting perpendicular to the section. The shear stresses increase from a zero value to a maximum value at the edge. All along the radius, the directions of these two shear stresses are perpendicular to each other. Here we look at an example involving torque and circular members. So this is a hollow circular member with the dimensions given. The maximum stress acting on it is given. The torque is not given. We are asked to find the maximum stress acting on a solid bar, which has the same volume as this hollow bar, and on which the same torque is being applied. So to start with, we'll find out the torque that is being applied in this hollow bar. Given that we have the dimensions, we find out J. We also know tau max. So from this equation, we find out the torque acting. Now this same torque will act on the solid bar. The volume of the solid bar is the same as the hollow bar. So the area of the hollow cylinder is found. And that area would also be the area of the solid cylinder, from which we find out the radius of the solid cylinder. So now we have the geometry of the solid cylinder. We also have the torque acting on it. So we can find out maximum shear stress acting using the equation tau C by J.